glitches with my camera. Just as I was joining, it seemed like PowerPoint had it captured instead of Google Meet. So hopefully everything runs smoothly here. All right, I created a new MATLAB assignment this morning and posted that on Moodle. Let me show that here. So that's assignment number 4. It's actually in next week's section. And it's going to ask you to do a whole bunch of different steps in MATLAB. And I'm instead of going over it in class explicitly, I'm going to give you more guidance. So you're going to need to operate a little bit more independently. And that's on purpose. As we're going through the course, you should be able to, create these exercises more and more on your own. Of course, if you have any issues with these, please come and see me virtually during office hours. And if you can't make my normal office hours, make an appointment. A few of you all are behind, and please get with me to figure out how to get you caught up and successful in this course. It's a required course for electrical engineers, and I want everyone to graduate on time. I have to take this again and that type of thing. So this time you're going to be able to use some more built-in type functions. So you're going to do a pulse amplitude modulation, a phase shift keying modulation, and a quadrature modulation. So MATLAB has functions to do all of those and to also demodulate those. And then, as communication engineers, we'll build up a whole system, and then we will want to count how many errors we have in the communication process based upon how much noise or other impairments that we might have in the system. So I've given you some links here to explore on how to use some of these things, including how to generate a scatter plot, which will allow you to show the constellation, similar to the kind of more crude or abstract drawings that I have in my PowerPoint presentations and all. So, and then I'll give you some information on how to generate some raw data, and then how to, ultimately compare it. And so you can do something like this. You can ultimately, create the input data, calculate the output data, and then check them, right? So MATLAB will operate on a matrix or a vector level when it's possible. And so this statement here, since both I data and O data, output data, are vectors, then it will compare all of those element by element. And so element 1, input and output will be compared, element 2, input, output will be compared, and so on. And then you can sum all that up, and that should give you the number of errors. Of course, until we start adding noise or some other impairments, you shouldn't have any errors. A couple of caveats here. In number 7, I ask you to change like the transmitter to gray coding, but leave the receiver to demodulator using just kind of straight binary coding, where it just assigns the symbols in bit order instead of this gray coding that we talked about last week. And so that mapping now is going to be very different. And so you should get a bunch of errors. And you should, as you go through this, you should understand why, right? As you get your hands dirty with it. And then, go ahead and change both the demodulator and the modulator to gray coding, and you should see that the errors return to 0. And then I ask you to add noise. The easy way of doing that is just to use this AWGN function. We might at some point show you kind of what's going on behind the scenes on that, how you can take your signal and calculate the energy of that, and then create a Gaussian noise process with the appropriate ratio of power. In this case, I'm asking for 20 dB, but then also do it at 12 dB. And what you'll see is that, maybe in the 20 dB situation, you'll have some messiness in the constellation at like 64 QAM, but maybe you could see how you could still receive some signals. When the signal to noise ratio is lower, meaning that there's lower signal power or higher noise power, then you're going to see that 64 QAM is going to be really hard to achieve good communication. So, all right, and then you're going to generate lots of plots and that type of thing. But hopefully we can still get all those submitted via Moodle and whatnot. All right, so there's a job fair next Tuesday. You guys are seniors. I expect you to be actively interviewing if you're not already committed to going to grad school and that type of thing. So, understand you may want to be jumping out of class early to get there. If you have reason to miss the class, please let me know in advance. And that way I can, obviously you'll watch the recording, but I can keep track of things, right? So, but hopefully you can make class and then run right to the job fair. All right, let's gonna move pretty quick here. Let's look at this presentation. And okay, hopefully. All right. Hopefully you're seeing everything there. So we talked last week about pulse amplitude modulation. We looked at it, we've reviewed it. So hopefully we understand that. You'll see that QAM kind of builds on PAM and so on. So if you're not fully understanding and comprehending everything, hopefully as we go through, the gaps will start to fill in. But instead of just doing amplitude modulation, let's do some phase modulation, right? So we talked about how we can manipulate the amplitude, the frequency, or the phase of a signal, right? So let's look at this kind of approach where we have this low pass equivalent circuit, where then we know we can extract out the actual RF waveform by multiplying by this carrier frequency, e to the j 2 pi FCT. That's a complex exponential, right? And then we take the real part of that, and that should return us the actual signal that we're dealing with. But it allows us to kind of focus on this low pass equivalent circuit here. And we see here that we've got this pulse, this G of T, and we've been not saying a whole lot about what that pulse looks like, but that it's multiplied in this case by this phase term, right? So e to the complex value is going to give us a magnitude of 1, but a phase, right? And phase is represented by the argument here, right? When we have a j, and then a real argument, that j makes it imaginary, and so this is a E to the J represents a phase. All right, so we've got 2 pi radians around a circle, and we're going to say that we're going to distribute m points, constellation points around that circle, and then we'll iterate from m little m equals 1 to cap m. And you can see that here, if we plug in m of 1, that's going to be 0, so it's e to the j 0. But if we plug in larger and larger values, then we will rotate around the circuit. By the time we get to m, it's going to be m minus 1 divided by m. So we'll almost return all the way around the circle, right? So if we plug and chug here and we take the real part of that, then where the sine term of these exponentials goes away using Euler's formula, and we're left with cosine, where here this is the RF part, and this is the phase that is modulating this more constant carrier right here. Okay, and then we can use some double angle formulas. This is cosine of theta 1 plus theta 2, let's say, and then you can expand that out. And so this is just the trig identity associated with double angles. And so we'll have a cosine of one argument times cosine of the other argument minus the sines of those respective arguments also. So, oops, wrong way. So I think I started showing these at the end of the lecture on Tuesday. So here we can assign m equals 2, meaning k is going to be 1. And so we might map a bit of 1 to a 0 phase, and a bit of 0 to pi radians phase, or 180 degrees, right? And so we can observe that, well, that's not really any difference at this level from pulse amplitude modulation, right? The constellation looks the same. And in fact, this we call this binary phase shift keying, or BPSK. And so that is functionally equivalent to pulse amplitude modulation. By custom convention or whatever, we tend to call this BPSK rather than PAM, or the pulse amplitude modulation, even though it looks the same. Then if we start increasing the M, or now we'll have 4 different symbols. Now we have a K of 2, so we can encode, take 2 input bits and map those to a single symbol, one of these 4. Right? So if we got 0, 0 coming in, we'll put it right there. If we got 0, 1 coming in, we will put it at pi over 2 radians, or 90 degrees, right? So now we're in the complex plane. And you see we're nicely evenly spaced between all these. Remember last week we started talking about the distance between constellation points and how that helps us understand how immune we can be to noise, where noise might cause us to make a incorrect decision on what symbol was actually received, right? And note that, is this gray coding here? Yes, it is. So if you pick a constellation point and you look at its nearest ones, right, that would be this one and this one. This one's a little farther away, right? So that distance is farther than these distances, right? And so when you look at the nearest neighbors of any given symbol, you see that the bits only change by 1, right? So here 0 to 0, 1, only that bit is changing from here to here. Only this bit is changing from here to here. Only that bit is changing, and from here to here. Whoops. Only this bit is changing, right? So now let's go to 8, right? So a lot of satellite systems use octal PSK, and that's actually due to the fact that The magnitude of all of these is 1, right? So if you draw a vector from the center here to any of these constellation points, that amplitude is the same, right? We'll call it 1. We'll normalize it. If it's 10 watts or 30 watts, we'll just kind of normalize it all. And we see that no matter what symbol you're transmitting, it's always the same power level. And that's, as we talked about in the last exam, that makes it easy to amplify. Won't go into all the circuits, reasons, and that type of thing. Just kind of log that in your brain, that when you have a constant power, constant envelope, right? So when you look at that RF signal, yes, you'll have a varying signal, but the max and min peak to peak value of that cosine wave doesn't change, right? So if it's plus or minus 1 volt, it's always going to be plus or minus 1 volt. The way we're encoding the information is by changing the phase. So when you have that constant envelope, that is much easier, much cheaper, much more efficient in terms of power to build a power amplifier. And when you put something up into space, power is everything. It's really hard to get enough energy in these things. And then also, if you're not efficient, what power you're putting in, the power that doesn't come out, right, because you're not very efficient, is dissipated in the heat. Well, in space, there's really hard to get rid of heat because you don't have any airflow moving across your components. So heat dissipation ends up being a really big deal. So just driving home the point that these PSK type waveforms have some really important advantages in a lot of situations, right? So here we've gone to 8. You can verify also, I believe that this is gray coding also. Pick any individual symbol and look at it. Okay, so now let's look at some quadrature amplitude modulation. So we went from PAM, where everything was on the real axis, to PSK, where we started having things in the complex plane, but everything was arranged in a circle. QAM is going to kind of take a little bit from both of those different things, right? So let us continue exploring options when modulating 2 orthogonal carriers. Let's take a carrier that we're going to modulate in a real sense, and another one that we're going to modulate in an imaginary sense, right? So they're going to be orthogonal to each other. Remember back several lectures ago, we talked about this a little bit with IQ type modulation. Okay, so now once we're in a complex plane, we could potentially place these constellation points anywhere in the complex plane. Now, it may not be advantageous to be totally arbitrary about it. So how might we organize that and why? Well, ultimately, it's going to go back to this issue of being able to efficiently amplify things and at the same time be able to have all of our constellation points satisfying this minimum distance type requirement so that we get really good performance in the presence of noise, right? So it's a bunch of words. Hopefully it'll become clear as we go through there, right? So here we've got kind of a combination of pulse amplitude modulation and PSK. Now we're still kind of arranging things radially or in an angular sense, but now we've introduced some different amplitude levels. So here, this is another way we can implement an 8, M equals 8 type of constellation. Instead of trying to squeeze 8 of these all around in a single circle, let's do 2 circles, right? And you'll see that we're still attempting to keep most of these points pretty far apart, right? So here, these guys are kind of, maybe you could call that a cross or a plus sign. And here, these guys look more like a square. They're really the same. It's just they're rotated relative to each other, right? And of course, this one is smaller amplitude. But this inner circle was rotated the same as the outer one, then we would be really close at some of these points here, right? So like this constellation point might be right there, and then we'd be close. So we're arranging this so that we are trying to get still maximum distance between all these constellation points. You see something similar here. We've gone to 16, and now this one is shifted from this one, which is shifted from this one and shifted from this one. You can count those up. I haven't labeled these with the gray coding, the bits or whatever, but if you've got an M of 16, then if you take a log base 2 of that, you get K is equal to 4. So each one of these constellation points would be encoding 4 bits, right? So if you're needing to send 4 bits, you only have to send 1 symbol instead of having to send 4 symbols. Again, we're calling that bandwidth efficient modulation. All right, now let's get carried away here, right? So here we've got a QAM. Actually, in the next presentation, I've got a little bit better animation of that. So let's get to that one. If I can find it, there we go. So, all right, and I actually probably have to. Let me just share my whole screen. All right, making sure we're in the right lecture here. Okay, so we'll look at QAM, and then maybe we'll get to FSK and some memory-based modulation. So we already kind of covered this. Now let's look at QAM. So in PAM, we were all aligned on this real axis, right? And now we're going to space it on both the real and imaginary axis, or in the complex plane. Again, we kind of like this idea of balancing things about 0, so that overall, maybe sometimes we've got maybe some negative voltage, some positive voltage, but they on average are going to kind of cancel out. In terms of energy, which is really more what we're interested in, these are all kind of constant energy, right? So they're the same distance away from this center. Now that doesn't hold once we start adding these guys, but these guys have more energy than these closer ones do, but they're still relatively balanced, right? So on average, things are going to balance out. So here's a QAM. It's not very common because it does look a little bit unbalanced. So if we're going to go to all the trouble of doing this, we might as well go here, right? And so it takes the same amount of energy to send this guy as it does to send this guy. A little bit more energy to send that guy, but not a big penalty, right? Again, that is related to the amplitude from the origin, and of course, then to get to energy, we're squaring it, that type of thing, right? So, but here we've got 16 of these constellations. Oops, wrong way. Here's 32. This is not a very common modulation also either, but the 64 one is. And so you can see that we're just kind of expanding it and expanding it and expanding it. So some communication systems, Wi-Fi and LTE or 5G, they all use quadrature amplitude modulation kind of inside a more complicated waveform that we'll talk about in a few weeks, called orthogonal frequency domain multiplexing. But in kind of inside that overall wrapper of OFDM, they're both using QAM, and we go up to 1024 QAM or even 2048 QAM, and then things are perfect, ideal, we can even go a little bit higher than that. So now here at 64, what's log base 2? 64 is 6, I think, right? Yeah. So each one of these constellation points, you're sending 6 bits of information, right? If you go to 1024, that's 10 bits of information that you're communicating using one constellation point. But as I showed these things here, I'm increasing the energy, the max energy each time, right? So you're either having to send more power, or if you are constraining that power, that energy, then you're having to squeeze everything closer together, which again, we've got this distance metric, the minimum distance between any of these points, right? And this is pretty well balanced, but we see these minimum distances between these. If we're constraining this outer part and we're trying to go from 64 to 128 to 256 to 512 to 1024, you can see that things are really going to get squeezed together. So we've got to have phenomenal noise, minimum noise performance, or a very good signal noise ratio, which might happen if we're really close to each other, like we are in a Wi-Fi type situation. Right? So, all right, let's expand this another dimension now. So we went from the real axis to the complex plane and showed a couple of different ways of placing things within that complex plane. But now let's consider that we can operate at multiple different frequencies, and we can break things up in time. Well, we've already been talking about how to break things up into time. I mean, we send a pulse, and then we send another pulse, and we send another pulse, right? Those are symbols. Those are the symbols that we're sending. But we could also send a signal in this frequency band, and maybe in this frequency band, and so on, right? So we're achieving higher dimensions by subdividing into these frequency and time slots, right? And we can modulate a complex signal in each slot. So now we're in the complex domain in both time and frequency. So that kind of begs the other remaining issue here, is that we've looked at amplitude modulation and phase modulation. Let's look at frequency, right? So we looked at analog FM and just kind of mentioned that phase modulation, analog phase modulation, is very related to that, right? So here again, we're going to work with this kind of low pass equivalent representation of the signal, and then to get the real actual signal modulated waveform, we multiplied by a carrier frequency at FC. Again, that might be 1 megahertz or a gigahertz or something like that, right? And then since that's complex, then we take the real part of that. We're going to get some cosine 2 pi FCT, right? And so this low pass equivalent circuit is going to be modulated to some version of itself using this M over this period T, right? And then that'll include one pulse, and then the next period will send more data, right? So now if we plug in a delta F term here, right? Only focusing on this SML, the low pass equivalent of it. This is your energy term out there, right? So we're just scaling that, so we have a signal with energy of this epsilon here when we square it and integrate over time t, right? So All right, so then we're back to this S of M up here, where now we've multiplied by this complex exponential at FC, but then taking the real part of that, right? So now we have a cosine with this kind of constant term here, 2 pi FCT or omega CT, modified by this modulating waveform. All right, so excuse me. So we want again these signals to be orthogonal so that we can easily extract out one symbol and not have it interfering with other symbols, right? So that orthogonality condition is if we multiply two of these symbols together and integrate from 0 to t, and we'll take the real part of that. That should give us 0, right? So if you take a cosine and a sine waveform and you integrate and you multiply those together and integrate it from 0 to t, it's going to give you a value of 0, right? So, and that should hold for any m and n pair, so long as they're not equal. If they're equal, then we'd like that to integrate to 1 if it's orthonormal, right? Or just some constant. So here's another way of writing this, right? So now we've got the energy out front. We've got these two terms here where really the only difference is this m versus n there. And to be proper, we're doing the complex conjugate over here, right? So and so now we can combine these two, right? So they're the same base raised to an exponent, so we can they're multiplied, so we can just add the exponents. But because of this complex conjugate, this gets a minus sign out front of it, right? So that's why we have an m minus n here, where all these other terms are the same. So not going to go into all the details, but if you integrate this, you're going to end up with this sign of an argument over the argument, right? So you've surely seen this type of form before when you did your signals and systems course and you looked at like the Fourier transform of a rectangular function, which is really what this is, right? So this is 0 to t, so it's 0 elsewhere, right? And so it's finite, but this has a magnitude of 1, so that's why we end up with this form right here of this when we integrate it, right? So all right, and then we can take the real part of this, and this complex exponential turns into a cosine. All right, so lots of math there. And then we recognize this as our little shorthand of this this sinc function, right? So actually this turns out to, considering that these are integers, you'll see that this cosine term is always going to be 1, I think, right? So all right, so for this SM orthogonal to Sn for every m not equal to 1, if and only if, right? So here we want this to now introduce this orthogonality condition, right? So while we've gone through all this, right? So we want this argument here to evaluate to 0, right? So again, that's this orthogonality condition. Well, we went through all that math. And so here, this is the condition that makes those things orthogonal. And if we draw this out, this sync x type function out, we see that when the argument is integer version of pi, it's going through 0. Halfway in between those steps, along with that 0, there's kind of a maximum value, right? So the sync x equals 0, where x is plus or minus k pi, where k is any positive integer, right? So where, you know, by putting a plus and minus sign out here and saying it's a positive integer, we're kind of excluding 0, but still accounting for the plus and minus versions of those, right? So so now we just substitute in this argument here and set that equal to plus and minus k and pi. So we can cancel out some pi's there, and we can say that this general solution here, where delta f is equal to k over 2t, right? So what does that mean, right? So if we have a large set of different symbols that we're trying to send using this FSK modulation, then we want the frequency spacing of all those to satisfy this 1 over, you know, or k over 2t. Now, if we're pretty far spaced in frequency, then you know, we're going to satisfy that. But let's consider what is our minimum frequency spacing, right? So that occurs when k is equal to 1 over 2t. So what we're saying here is that that is the closest that we can step in this delta f when we're modulating these bits using this FSK modulation, so that we don't have any overlap from one frequency step to another. So we can clearly distinguish the different symbols from each other, right? So actually, let me go back to this kind of idea here. So what we're saying is that we're going to maybe from, you know, FSK using this kind of format here, at one time we might be in this frequency slot, and at another time we might be in this frequency slot and this slot and this slot, right? So what that is doing is that it's modulating the bits into one of 4 different symbols, right? And that means we can modulate 2 bits into this m equals 4 FSK type modulation, right? But if we're too close to each other, then our energy is going to leak into these other slots, right? And then we're going to have a hard time distinguishing them, right? So, all right, so that's the big takeaway. I might put this formula on the formula section of an exam and ask you, you know, given t, what's the closest frequency spacing you can have in an FSK waveform, right? So note that the modulation of FSK is inside the cosine term, right? Let's go back here, right? So here we're modulating, but it's inside a cosine term. So it's not linear anymore, right? And if we add two signals using QAM, or more that QAM's kind of the general approach, but PAM or even PSK, the signals add linearly, right? FSK is an example in nonlinear modulation, right? M is commonly 2 for simple systems. So we're just doing 1 bit per 1 symbol. So we have 2 different frequencies that we're using, but can be much more, right? So, maybe in the older days, you would see FSK used in some Internet of Things type applications, industrial communications type applications, that type of thing. All right, so that's frequency shifting modulation, and again, the key here is that we're modulating it into different frequencies by time, right? And each of those frequencies you kind of assume is a little slot, right? You want that waveform to be mostly in that slot, but it leaks out, right? But if we are spaced such that, well, there's one slot, there's another slot, there's another slot, right? Then we might have, let's see if I can do some drawing here, right? So, our other slot might show up like this, right? And so where it's at a peak, this other one has minimum energy, right? And same thing here versus there. We might have another slot right here, and similar type of things, right? So where there's a peak, all the others are crossing at the 0. This guy's at a peak, all the other waveforms are going to be crossing at a 0. Same here, right? So that's kind of a common theme in signals. You'll see it in other contexts where when we get to orthogonal frequency division multiplexing, we're going to see this same type of pattern going on, right? So that's kind of the easy test question. This is the concept that we're really dealing with. And yeah, there was a lot of math to get there, but that's the takeaway that I want you to have, right? So now all those were memory-based, memoryless modulation, right? So whatever set of K bits we have coming in, that got mapped to a particular symbol, right? And then that symbol got transmitted. The receiver looks at that symbol, tries to figure out which symbol it represents, tries to figure out based upon what it sees, what it measures, what did the transmitter actually send. And then it can map that symbol to those, same 3 bits. Now they're output bits, but hopefully they match what the input bits were. But that's kind of on a instantaneous basis, right? So if we have a K is equal to 3, M equals 8 type of system, then we pick off 3, that get mapped to a symbol. Then we take the next 3 and that gets mapped to a symbol, right? Each of those mapping is independent of whatever came before or whatever comes afterwards, right? Now we're going to change to memory-based modulation. And we're going to talk a little bit about Markov chains. Markov's another term, especially if you go into graduate school or you work with time-oriented systems that evolve, right? So that are dynamic. You're going to run into this guy Markov quite a bit, right? And Markov decision processes are huge in reinforcement learning and AI. Markov chains we use in this modulation, right? So I'll talk a little bit about non-return to zero and non-return to zero inverted baseband signals, and we'll talk about trellis modulation, right? So I had these little equations in a previous lecture. We're looking at an output or modulation function, right? Where here we have some input bits coming in, and we have an existing state that we're in, right? And so we're in some prior state. This is L minus 1 here. And then we get in this new I sub L, all right? So a new input bits. The combination of those through some function results in a modulated symbol, right? At the Lth time step, all right? At the same time, we have a state update relationship where we take the prior state, we take the input bits, and we have a function that moves us to a new state, right? So we have outputs and states. This should be, reminding you of kind of your second half of your digital logic course where you did all that FPGA, Verilog type stuff, right? So you studied these state machines there. All right, so let's look at these memory-based modulations and introduce a non-return to zero and a non-return to zero inverted, right? So let's look here where if we have, I think this is a map such that okay, so these are recording the outputs here. We've got this type of relationship. So we are looking at the new bit, and we're exclusive ORing that with the existing bit. I'm trying to look at this to see if this makes sense, right? So if we're in a 1 and we get a 0, I think that's the NRZI, and we're going to stay there. So so in this case, what we see here is that we have a transition when we have a 1 value, right? And so in this NRZI version, but when we have a 0, we don't change, right? So so we're down here, we get a 1, we transition. We get a 0, we don't transition. We get a 1, we transition. We get another 1, we transition. We get a 0, don't transition, don't transition, don't transition. We get a 1, we transition. Okay? So there's this way of looking at it. We've got our BKs coming in, right? So that would maybe be this mapping, this waveform right here. And so that might go through some decision process where if we're a bit of 1, then we output a signal that has a voltage of plus A, right? If we get a bit of 0, we output a voltage of minus A, right? So that's what is interpreted there. But instead of just doing that based upon our input bits, we're going to apply our input bits as this A of K and go through this exclusive OR type operation, or this transition thing to actually get the symbols that we're going to send, right? So these are technically the symbols once they've been added, converted from logical to actual voltages, but AK are the bits coming in, and then we modify those with BK. So here we're remembering what we had before, right? We're remembering this BK and BK minus 1, and we're outputting a BK that is a function of both that previous state and the input value, right? And then in this case, our output is basically the same as our state update type equations.
Professor, quick question.
Yeah.
Can you go back to the slide?
Yes.
Can you explain how you got the non-return to 0 for the drawing? That drawing.
How I got the what?
The drawing.
This drawing
the
up
signal.
here?
The signal. Yeah, the signal for the NRZ.
Yeah. So this NRZI here is calculated using this. I'm now questioning my NRZ here, but because that's I'm not exactly sure that I would call that NRZ, and I did this drawing last year. I'm not sure where I got it from, but this so maybe ignore this part up here, and we'll focus on this, right? So we have these bits coming in. So these would be our AKs down here, right? And then we're going to use this equation, right? And so if we're at a 0 and we get a 1, well, the exclusive OR of that is a 1, right? So we're going to change every time we see a 1 here. So if we're at a 1 and we get in a 0, then that's still a 1. But if we're at a 1 and we get a 1, well, 1 exclusive OR with 1 is a 0, right? And so we drop down to the 0 level. Then we get a 1, but we're at a 0, so 1 exclusive OR with 0 is going to give us a 1, and so on. Okay. So we're really implementing this equation based upon these inputs, and then this is representing both our state, our current state, or previous state. You know, it would be this is our previous state matched up with the new input, right? Previous state matched up with our input, right? So it's K minus 1 for the previous state versus K. And then this is what is outputted, right? So the next one is what is outputted right here, right? So we actually won't work specifically with those type of things, so don't want to emphasize that too much, but let's look at Markov chains in concept now and define those, right? So here we have a discrete time and discrete valued random process, right? So it's random and it's taking on discrete values at discrete time steps, right? So its current value depends on the entire past values only through the most recent values. Now, this is always something that I kind of struggle to master in my brain every time I come back to Markov chains. So what we're meaning here is that, yes, our current value, so this is going to be a dynamical process that updates at each time step, each discrete time step. We are going to evolve this random process, this discrete valued random process. So its current value depends upon all of the past values, but we only have to look at the most recent values, and maybe in the strictest case, in the most recent value. Okay? Now, what does this mean? We can look at the probability of this xn as conditioned upon all of these prior values, right? So looking at all these out to this n minus j. Now, what we're saying here is that there's a finite length to this, right? So this would be this kind of first part of the sentence, right? Upon depends or is conditioned, right? This conditional probability. So the probability of your current value of this random variable taking on a particular value is conditioned upon all its past values, dot, 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 out to forever, right? So the entire past values, but only through some set of most recent values, right? So we can actually only have to look out to these J previous values to understand all of that, right? So whatever was happening out here at something greater than J is somehow kind of folded into these results here, right? Okay, so this would be what we call a Jth order Markov chain or process. The current value only dependent upon the past Jth values, right? And a lot of times J is 1. Okay, so in this case, here we have a state transition diagram for this NRZI, right? And non-return to zero inverted. So here we have a state transition diagram describing the outputs for a given state and transition rules giving the current state and the input, right? So here we have a state 0 and a state 1, and we have some inputs that come in, and we'll, we will transition from one state to another depending upon what we get, right? So if we're in state 1 here, where maybe state 1 is mapped to a 1, as we kind of had before, we get a 0 in, then that if we're using that NRZ, that exclusive OR type of relationship, 1 ORed with 0 is still going to give us 1. So we're going to just kind of return back to this same state, right? So this would be our transition. It's just a diagram that says we stay there, right? And then here we're if we get a 1 value in and we're already at 1, we'll transition to state 0, right? State 0. And if we're in state 0 and we get a 1, well, that exclusive OR puts us over here to state 1. But if we're in state 0 and we get a 0, we're going to stay there, right? You can work this out. This is that exclusive OR type of relationship of your existing state, your prior state, and the new input value, right? And then on the other part of this, these transitions, we show the outputs that we're sending. And basically, if we're in, we're going to arrive in state S0, either by just staying there or transitioning there, we're going to output a minus S of t, right? Some symbol that's a function of time, right? Some pulse, right? But it's going to be, in this case, a negative, versus if we're in state 1 as our new state, we're going to send out the positive version of that, right? So so this shows us the state transition diagram here. Now, another way of writing this is to write it as a trellis, okay? So this is equivalent to this, using different notation, different terminology, but this is nice for when we start expanding to several states instead of just 2 states. We can keep adding states below it, and then when we actually get to discussing the Viterbi algorithm, then we'll use this type of trellis here. But the important thing is that it's just being rewritten as a trellis, right? So now the state is represented vertically, right? So we've got a state 0, a state 1, we could have a state 2, and a state 3, and so on. Right. So every time we're going to add a state or a few states, we're going to kind of expand this trellis vertically. Right. But moving to the right is kind of reflecting a time step. Right. So here, this might be time 0, and we're going to be in some state. Let's say we're starting here. Then we're going to have some input values, and we're going to transition. Well, if we're in state 0 and we get a 0, then we're going to stay in state 0. We're going to transition to there, right? At our next time step. Okay, so this would be, t equals maybe cap t. Right. So, but if we're in state 0 and we get a 1 in, then that exclusive OR is going to give us a 1. So we're going to transition to state 1. But if, let's say we started, we can go over here and say we're in state 1, then we get in a 1. We're going to transition. 1 exclusive OR with 1 is giving us a 0, so we're going to transition over here. So what we see here is that, well, this, what I kind of hesitated. Do I start here or do I start there to describe this transition? Right? They're the same. Right? So they're just at a different time step. If I'm here, I'm in state 1. I get a 1. I'm going to transition to this state 0. That's exactly the same as I drew there. I could draw it right there, right? So this trellis is essentially replicated at each time step, right? And so we can see how something might evolve over time and based upon different states that it is experiencing the state and the input data. So you might see something that evolves like this, right? So so this gives us a little bit of time history, whereas this just kind of gives us a snapshot in time, right? That's why oftentimes we use this trellis in communications, especially when there's this memory involved. All right, so let's go back. How much time do we have? 15 minutes, give or take. Note that the FSK, similar to PSK, has a constant amplitude, right, or constant envelope. And the phase can change arbitrarily and abruptly at the symbol transitions. So we're going to change frequency. Well, frequency and phase are related through a derivative type of relationship, right? So if we change frequency, then our phase is going to have a discontinuous arbitrary change, right, at these symbol transitions. So let's think about this. Let's think about this in a context of what we learned about Fourier transforms. When we have things that change quickly, then that implies a wide or high frequency content. Okay, think of a cosine wave signal that changes fairly smoothly and fairly progressively, right? So then what is the Fourier transform of that? Well, that's an impulse, right? Or a Dirac type function. in the frequency domain, meaning that all of its energy is tightly constrained in that frequency range. Contrast that with a square wave, right? When you did the square wave and you looked at that in the time domain, you did the Fourier transform of that, what did you get? What did you get as a result? Well, you got that sine x over x type shape that we saw a few slides ago, right? When we were looking at the orthogonality condition of FSK, right? So there in a square wave, you've got things that change abruptly, right? And so there we know that at sync X, actually those little, you know, side lobes, we call them, go off to plus or minus infinity in terms of frequency. And so you're spreading all that energy out through a lot of different frequencies. Another way of thinking about it is take that cosine wave, and let's take a low frequency one, where now the slope as it's kind of going through zero is shallow, and that corresponds to a low frequency. So even though our frequency is constrained to this Dirac or impulse function, impulse in the frequency domain, so it's at a low frequency. But if we squeeze those sine or cosine waves together in a time domain, then where it's crossing zero is getting steeper and steeper, right? That's kind of by definition what it means to be higher frequency, right? So then when we do the Fourier transform, that Dirac function showing up higher and higher in frequency. So just saying all that to just kind of help you remember that that relationship between the time domain and the frequency domain through that Fourier transform. When we have things that change abruptly or very steep in the time domain, that's going to be reflected in the frequency domain as a lot of frequency content, right? Just generally bad. Frequency spectrum is expensive, right? It's actually a finite resource, kind of. On a practical basis, we can't go to infinity frequency, right? So, spectrum is valuable. So we want to use it as efficiently as possible. And, we're encouraged to share it with others, either through a licensing or an unlicensed regime, because everyone wants a little piece of the spectrum, right? So, so that's just to motivate here, this next few slides here. Anytime you have something that changes quickly in the time domain, expect some spreading in the frequency domain, and that's bad, right? So in this case, we see side lobes or energy on the sides of the basic spectrum, right? So if we do something like this, where we're just kind of changing from one frequency to another, this is terrible drawing the mind, but this would reflect different frequencies, right? So that would result in an abrupt change in phase at each one of these, right? Each time we stepped it. So how might we mitigate those bad effects? Is we could use something we call continuous phase FSK, and I'm going to breeze through this. I want you to see it, but we're not going to spend a lot of time on it. But gives you an appreciation for kind of how we evolve basic modulation schemes to be more practical, right? So we constrain the phase to be continuous. This will eliminate the arbitrary and abrupt phase transitions and those resulting side lobes in the frequency domain. This constraint implies memory in the modulation, right? So if we're going to constrain the phase to be continuous, then we've got to remember, okay, from t, what was the phase, so that when we're creating the waveform at 2t, we can match that phase up, right? So we've got to have some memory. That's why we kind of took that little diversion to talk about memory a little bit, right? So, all All right, so we can start with this pulse amplitude modulated signal. I'm going to introduce some new notation here. There's lots of different notations, so I'm just kind of giving you exposure to something you might see in some of your other readings or in the industry. So here I would mean your information source coming in, right? And at time equals n, right? Nt, right? Where now our pulse is going to have this shape at from T to cap T and so on, right? So where this gets replicated, and what we end up with is a summation of all of these things, right? Where this input bit is multiplied by this pulse, and then we step to the next end and we do the same thing. We do the next thing. Now, generally, what we'd want is some pulse there, and then at our next step, a time, maybe we have a pulse there, and then maybe a pulse there, and a pulse there, and a pulse there, but then a pulse there, right? So these are all actually, okay, so that's, you know, for n is equal to 0, let's say. That's n equals 1, n equals 2. And so these guys will all get added up, but they're all stepped across in time using this kind of type of relationship, right? So let's see. Then, so this G of T is a pulse T seconds long with amplitude 1 over 2T. That's the balance energy out. So the summation over N and the NT term in G produces a train or sequence of pulses by overlaying a time-shifted version at each period T. That's what I just tried to sketch on the screen, right? So it denotes the mapping of amplitudes, right? So here, this I of n, this could be plus or minus 1, or could be a larger set of samples m, right? After mapping k bit blocks from the information sequence an, right? So so this is doing that kind of mapping from k bits to a particular symbol, one of m different symbols. Then so now for continuous phase FSK, let's define this F sub D to be the peak frequency deviation. Let this phi naught be the initial carrier phase, and the equivalent low pass waveform then. Now we're just looking at that low pass waveform. We'd need to multiply by the E of J 2 pi FCT, and then take the real part of it to get our actual modulated waveform. But this is that low pass waveform, right? So now we're going to have this peak frequency deviation, and we're going to have this pulse stream, and we're going to have an initial phase, right? And all this is in the argument of this complex exponential, right? So all this represents phase, but we're integrating from minus infinity up to a particular t, right? So, and again, we will normally have that discretized by this period cap t, right? So, so then, yeah, we convert it to the carrier modulated multiplied by the E of J omega FCT and take the real part, so we just have the cosine. And so we've got this RF portion, we've got this modulating portion, and then we've got the initial phase, right? So that's going to be constant. We were kind of representing this as this term right here. Okay, so another way of writing it out, right? So now we've introduced this dt as this summation pulse train. So the Integrand actually still contains discontinuities, but it turns out the integral is continuous, right? So if we look at this integrand, this guy still has these discontinuities associated with it, but since we're integrating it from minus infinity to t, we're going to convert that to continuous type waveform. So we can find the phase of the carrier in the interval of this particular pulse due to the modulation by integrating. So we can look at this and at a particular t and integrate that. So here we're introducing a bunch of more notation, and I've run out of time. So yeah, maybe we'll cover that. That was the end of the lecture anyway. So all right. So if I saw that most people had their exercise 3 turned in, if you haven't, please get that in. Send me a little note that you've done that. Try to get caught up. You'll lose some points because I want these things turned in on time, but hopefully not too bad. And again, if you're going to the career fair, if that your career fair activities are going to mean that you're going to miss all or part of the lecture on Tuesday, please let me know and start taking a look at the next assignment. Assignment 4, it's due Friday, and I'd like a little bit of feedback by Tuesday on whether Friday's a reasonable due date for that, or if we need to give it some more time. All right, have a great weekend.